In this lab, I observed the motion of a ball traveling at a constant velocity as it rolls along a carpeted floor. In order to describe the motion of the ball as a vector velocity, I used Newton's second law, which states that objects that are not moving at a constant velocity are affected by two components, the net force acting on an object and the object's mass over time. However, in this experiment, the ball is traveling at a constant velocity, meaning that the net force must be equal to zero. Let's look at the components of Newton's second law that make this statement true. If there was a net force acting upon the object, we would not expect to have a final velocity that is equal to the initial velocity. As previously stated, the only case in which v final equals v initial is when there is no net force acting upon the object, meaning that F net must be equal to zero. Using tracker, I analyzed the ball's travel as it moved from right to left. The coordinate system is oriented such that upwards is the positive y direction, downwards is the negative y direction, to the left is the negative x direction, and to the right is the positive x direction. Because the ball travels in the negative x direction, the positions recorded in tracker as well as the velocity of the ball are recorded as negative values. If I were to place the point of origin on the left of the screen, the x values of position and subsequently the calculated velocity of the ball would have positive values rather than negative. Having said this, the sign of the direction of travel doesn't actually change the value of the velocity, although it would change its sign. Regardless of whether or not the ball travels in the positive or negative x direction, the magnitude of the velocity vector will remain the same. The position versus time graph was generated based on the ball's motion, which I calibrated using the ball's diameter. The graph appears to be close to being linear, which would be the case if the ball was truly traveling at a constant velocity. A perfectly linear graph of the same experiment was generated by the position versus time graph of a computer model in which the object is moving at a constant velocity. The computer model describes the behavior of the moving object if all outside vectors were to be eliminated. The value for the initial velocity was found calculating the difference between the first two position data and the change in time found between the difference in these two times, and the average velocity was found by dividing the change in position over change in time. In Python, we can see the computer model generated. The net force vector is set as 0 in order to ensure that the object travels at a constant velocity. This is evidenced by the perfectly linear graph produced by the computer model, which we can see when we run the module. And taking the values generated by the computer model and putting them into a Google spreadsheet, we can see the experimental data as well as the computer data entered below. And here we have a graph that illustrates the difference between the position time graphs of my experiment versus the computer model of my experiment. The computational model plots velocity as perfectly linear and therefore constant, whereas my experiment data gradually diverges from the computer model as time elapses. Although there were no visible forces that could account for the difference between the velocity graphs, we can account for some factors that could explain the ball's change in velocity, including the force of gravity on the ball, the force of friction between the ball and the carpet, as well as between the ball and the air, also known as drag force. Had these forces not affected the ball's velocity, we would expect to see matching plots of the computational model and the experimental data, and thus prove Newton's second law.